Hello, everyone. This is the chapter 11, magnetic forces and the fields. We will solve some of the problems for exam 2. Okay. The first problem is cosmic ray proton moving toward the Earth with the speed of this velocity and experiences a magnetic force over 5 times 10 to the minus 16 Newton. What is the strength of a magnetic field if there is a 60-degree angle between the field and the proton's velocity? Okay, so we will use the formula that defines the force, magnetic force, for the moving charge for a given magnetic field. Okay, so it is here. So in fact, in the vector form, QV cos V. Okay. And then if you look at it, the velocity, speed is given. Okay. Proton means is that its charge is plus E, so that these two are given. And then forces is given. Okay. And then we want to find out what the B is. Okay. And then we can find out from this formula, B is given by this equation, and the F is known, velocity is known, Q is known, and as well as zeta is known. Okay, zeta is 60 degree. And then you can find the numerical value by plugging the numbers. Okay, but the thing is that you need to keep the unit is a Newton, and there's a Coulomb, meter per second. It's important. Otherwise, you will get the wrong answer. And once again, a cosmic ray electron moves with the speed to the Earth's magnetic field at an altitude where the field strength is this much. What is the radius of a circular path that the electron follows? Okay. So there are maybe, once again, we are looking at the force exerted by the magnetic field, but in these cases, what is important thing is perpendicular. So V is perpendicular B. And in this case, we know that it will make a circular path. Okay, circular path, that is important. And then in the case of a circular path, we can define the centripetal force, and then we can find out the radius. Okay, let's do it one by one. So the magnetic force is given by this one here. F is given by Q times cross V, but V is QV, I'm sorry. This is QV cross V. And then V is also orthogonal to V such that this becomes sine theta is 90 degree. Equal to 1, so that you get this one. Okay. And then for the circular motion, we know that the centripetal force is given by mv squared over r. And this should be equated. Okay. And then we have a magnetic force on the left-hand side, centripetal force on the right-hand side. So from this, we can find out r. So here the mass is known and charge is known. and the velocity is known, and the magnetic fields are known. And then you can find out R in this formula. But once again, we have to have a kilogram and meter per second, and then there is a Coulomb and Tesla. Okay, and then we can get meter. Okay, so that note that everything is used in this unit. Okay. What is the maximum torque on a 150 ton square loop of a wire? 18 centimeters on a side that carries 4.5 ampere current in a 1.6 Tesla field. This is once again important uh, situations where the loop, current loop, I with the A is the area, and it is, we have a certain normal vector, and then by current loop will generate magnetic dipole, and then this magnetic dipole will have torque. Okay, so magnetic dipole is given by n times its magnitude, NIA. Okay, and then we want to find out, this is that NIA B sine theta. Theta is angle between the magnetic dipole and the magnetic field. So this is the magnitude. So we note that the maximum over sine theta is 1. Okay. And then in this case, we note that torque is given by NIAB. So number of turns is given, current is given, right? And the area is given. So area is 18 times 18 with a square. 18 times 18. And the centimeter is 10 to the minus 2 times 10 to the minus 2 meter square. Okay. And then you can get orange 8 area is given like this, and then n in ampere, area in meter square, and b in Tesla. Then you can get the torque. Okay, torque is usually Newton meter. A wire bent into a semicircle of the radius of the 30 centimeter form a closed circuit and carries a current I equal to 4 ampere. Okay, so this 4 ampere. The wire lies in the XY plane and the uniform magnetic field that is directed along the positive y-axis. Okay, like this. Find the magnitude of a magnetic force acting on the straight portion of the wire. Straight portion. So here, this is the straight portion. Now let's try to find out. So if there's a wire that carries a current, and then the force on that wire is given by F is IDL cross B, the length L. So in the textbook, it is sometimes is called IL cross B, and its magnitude is given by this one. And now it's time to think about the L for the straight portion. The straight portion is the diameter of the semicircle here. Okay, diameter of a semicircle. So it says L is 2R, so it's a 0.6 meter. And then we need to find out the force, magnitude of magnetic force, so that we need to figure out current. Current is given. Now we have a L, B is given, and then it's time to think about what is the zeta here. So in this case, the wire lies in the xy plane, and the straight up portion is along the x directions, and the magnetic field is along the plus y directions. So that angle between the linear straight portion and the magnetic field is 90 degree. Okay. 90 degree, 90 degree. And then we know the numbers required, and that you can plug in current in ampere, and this is the length in meter, and this is the magnetic field in Tesla, and then this is what we get in Newton. And the direction is that if you think about L is plus, along the plus x direction, and B is along the y direction, and L cross B is plus g directions. Okay, so it is out of page. So that means this is the force is toward you. It's out of the page. Okay, now similar situations. Find the magnitude of magnetic force acting on the curved portion of the wire. So it's going to be interesting to take part in the straight portion and the curved portion. Okay. So the formula will be the same, but in this case, we have to have some integrations. So dl in this case is, if you take that this is the zeta, dl corresponds to r d zeta, and then zeta is 0 to pi. Yeah. So that's the thing we need to understand. For the small current element dl, which is the dl, yeah, note that the vector component is the zeta direction. Okay, dl cross b, and then f is going to be along the arc integrations, and we'll find out. This would be interesting because we note that b does not depend on the position, so that we can take out the integral. And then we are going to find out what it is. Okay. So this is the, let's call it as a net displacement vector from the start to the end, which is the delta IL. And then we have this one. So it's time to think about how to find out delta R. So semicircle, we have a right end and the left end is given by this one. And delta R is, in fact, the curved cut goes from the left to the right to the left, such that you will have this one. So if you get this one, so we are conservative system. This is going to be same as this one. Okay. So even though you integrate over the arc all the time, then there will be some cancellation. And in the end, what you get is this one. And it's going to be minus 2R times I. And the magnetic field is along the plus Y directions. So once again, if you do it, this is also K direction. So that means is toward you. Okay. F is 2ILB, and then if you look at it, it is once again is toward you. So this is also moving toward you, and this straight part is also moving toward you. But if you compare that, and then you'll find out it's going to be ILB, sine theta is 1 for the straight part, but for the circular part is 2 times ILB. So it's a factor of 2 comes in. Because of the whole length element would contribute to the force. Electrons are accelerated from the rest through the potential difference, and the electrons travel along the curved path of the radius 7 centimeters because of a magnetic field exerted on them. So that there's a magnetic field, the charge. If the magnetic field is perpendicular to the beam, what is the angular speed of the electron? The mass of the electron is this, and the element charge is this one. So once again, it is the charged particle moving in a circle by the magnetic field. And then if it is moving in a circle, then we can apply the classical mechanics law of this angular speed. Omega is given by V over R. V over R. Okay, as you might remember. So let's start with the velocity first of all. So if you look at it, is from the rest through the potential difference of a 300 volt. So that it starts from this is the potential energy, and then this is the kinetic energy. So potential energy becomes kinetic energy. And from this, we can find out velocity. Okay. And then we can put those numbers. But once again, we have to be careful of the unit, volt, coulomb, kilogram. And then you can have a meter per second. And then in the case of a circular case, the angular speed for the circular motion, we all know that omega is V over R for circle. This is V. and this is the omega. Omega is V over R. Then we know what the V is, and we know what the radius is. And then we can find out the omega. Note that this is the radian per second. Okay. And here comes, once again, it's a wire. Here's the wire. Wire section has a certain resistance. Is connected to the conducting wire of the negligible resistance to a 7.5 battery. The wire is located in a uniform magnetic field B directed perpendicular to the section of the wire. Calculate the magnitude of B when the force on the wire due to the magnetic field has a magnitude of this one. And in this case, it did not say anything about the current, but you can find out the current from its resistance and the voltage. Okay. So first thing is that we are going to utilize Ohm's law. So its current is given by voltage difference divided by the resistance of the material. And then here, voltage is given and resistance is given such that current is given by this ampere. And for the given ampere, then we have a current wire, current carrying wire under the magnetic field. So magnetic field will exert a magnetic force on the wire given by this one. And note that we say that it's perpendicular. So that's theta equal 90 degree. So that we have this one, okay? And then if you look at carefully, the force is given, Newton, in terms of Newton, so that we need to find out magnetic field, okay? So Newton, ampere, and length in meter, then you can find out the Tesla, okay? Okay, this is the way to do it. A proton that is accelerated from rest by a potential of 13 kilovolt enters the velocity filter consisting of a parallel plate capacitor and the magnetic field. Okay, here. The electric field between the parallel capacitor plate is about this, and the B field is required so that the protons are not deflected. What is the magnetic field? Required so that the protons are not deflected. Once again, we have now we have a interesting case where the both electric field and the magnetic fields are present. Okay, and if you look at it, the protons are moving in these directions, and then you can see that it is for the magnetic field, it is perpendicular plane, so that you will have a circular motion. Okay, and but in the case of electric field, you will find out it is forcing down. Electric field is this way is plus minus, so that proton is positive charge, so that it will move this way. But the magnetic field wants to keep it in this way, okay? So we have to have a certain balance between the magnetic force and the electrical force, just as in the Hall effect. So electric force on a proton is given by this. Magnetic force is given by this one, okay? And no diffraction means uh, electric force is in equilibrium with the magnetic force, such that this one. So if you just take out the Q here, both sides, and then you can find out E is given by this one. Magnetic field is given by this value. Okay. And if you go back, you need to, so electric field is known, right? The field is known here. We know electric field. But we need to figure out what the V is. V is calculated from the energy conservation such that this is the potential energy. And then this becomes kinetic energy. And then if you set it, the charge of proton is plus E, then you'll get this relationship. So we have a B. And then finally, we can get the magnetic field. So note that is a Newton per coulomb. Velocity should be meter per second. And then we get Tesla. Okay. A rectangular loop is located in a uniform magnetic field pointing in the negative x directions. So magnetic field is pointing in the negative x direction. The orientation of loop is shown below. Oops. I did not add the diagram, but the theta is given by 45 centimeters. And then if calculate the magnitude of a torque on a loop. So when we say about torque, then we have to come back to the this magnetic dipole moment, okay? And magnetic dipole moment with the U cross B is going to be our torque. And then if you take the absolute value, you get this relationship, okay? So we need to find out what is the area, current, and the magnetic field, and then we can find out the torque, okay? So we need to figure out the loop area A, first of all. So this is a rectangle. It's a rectangle, 2.5 centimeters on sides, okay? And then area of the loop in meter square. Note that it should be converted into meter square all the time. And then compute the torque. Then we know the current is ampere. Area is meter square. And B in the Tesla. And then we get this one, okay, Newton meter. Okay. So electron in Thomson's apparatus moves perpendicular to a magnetic field B along the path of a radius of 20 centimeters. If imposition of electric field makes the path straight, find B. Okay. The mass of the electron is this. Okay, once again, it is the charged particle on the magnetic field and electric field, both cases. And then in the cases, straight path means is that it does not deflect. That means electric force and the magnetic force are in equilibrium. Okay. So let's try to find out moves perpendicular to a magnetic field B. So it has R, radius R is given. And electric field magnitude is given. Okay. The mass is given, charge is given. So condition for the straight path is electric force, it should be equivalent to the magnetic force. Okay. Note that in this case there is no sine theta. Sine theta becomes 1 because its velocity is perpendicular to b. Okay. And no deflection means magnetic field should be same as the magnetic field force is same as the electric field force, so that we get this one. Okay. And then we get this one. Okay. But in this case, we need to know what are the other parameters we are missing. What are the other parameters missing? So in the magnetic field, initially it is a moving circular motion, so that magnetic force should be centripetal force. Okay, so that in this case, B can be found. Okay, oh, I see. And then from this B, you can find out, if you look at it, and then you'll see that if you just plug in to here, you'll see that E of B is given by this one, so that E is, if you just take the B here, and you can find from this relationship, so eventually, or we want to find out the magnetic field, right? Right. So we want to find out magnetic field. So in this case, B square is ME over ER, so that we can find out B is square root of this one. But you have to be very careful about unit. Electric field should be volt per meter, mass in kilogram, and charge coulomb, and radius in meter. Okay, so that's the way it is. Okay. 70, a large water main is 4.6 meter in diameter, and average water velocity is 2 meter per second. Find the whole voltage produced if the pipe runs perpendicular to the Earth's magnetic field. Okay, so this is the, once again, we need to figure out uh, the whole voltage. So Hall effect is the where the charged particles are under the influence of both magnetic field and the electric field. So Hall balance is matched by the magnetic field and electric field forces. That's the. And then what it is important to find out is that the question is find the whole voltage. Whole voltage. Whole voltage is given by electric field times D. Okay, so if you plug in this one, and then you can find out VB times B. EH is VB. And then if you plug in all the numbers in the meter per second, and the Tesla, and then here we go in terms of a volt. Okay. So it is a very simple problem if you know the whole condition, whole measurement condition, where the electric field and magnetic field are both present in the perpendicular manner. And then we need to equivalate magnetic field and electric field forces, okay? And then we can find out some of the relations. And then from this, we further applied these things. So remember that is a whole voltage is also kind of plus, plus, minus, minus. So the E, and then this is the voltage. And if the spacing is D, E is V over D, V is ED. Okay. So we have seen it for the parallel capacitor in previous chapters, right? 72, a flat copper ribbon of the thicknesses carries a steady current and is located in uniform Tesla magnetic field directed perpendicular to the plane of the ribbon. If the whole voltage is this one measured across the ribbon, and what is the charge density of free electrons? So that it is it's a fundamental or whole measurement problem. Okay. So whole effect relationship, so that we have some ribbon. Okay. And then there is a magnetic field. Okay. And then so electrons are moving in, and by if there is by this uh, magnetic field, charge will be separated, and then there should be electric field, and we need to have a whole effect equation. Is this magnetic field force, electric field force should be equivalent, so that we get this one. And the whole voltage across the thickness T is given by EH times T. Okay, that's the thing we have to understand, the whole effect equations. And then now let's try to find out what else we need to figure out. So, so in this case, we note that whole voltage is given by this one. This is E. And then our velocity is given by this one. Okay, so this is the drift velocity. And this drift velocity is directly related with the current. Okay, so this is the our density of a carrier charges, and its charge in coulomb, and area times your drift velocity. Okay, and then if you go back to these equations, and then you can have whole voltage is this one, and then in terms of n is the what we want to find. N is given by IB over QT VH. So all the elements are given, right? The current I, and magnetic field, this, charge, this, thickness is this, and the whole voltage given by this one. Okay. So starting from the Hall effect equations, we derive the Hall voltage equations, and then from the Hall voltage equations, we come up with the drift velocity (Vd), and then this drift velocity is related with the current. Okay, and then from this we can find out the charge density n. Okay, a proton moving in a circular path perpendicular to the constant magnetic field takes 3 microsecond to complete one revolution. This is the period of the circular motion, and determine the magnitude of magnetic field, so that we are given interaction of the moving charge and the magnetic field, and then we get our circular motions, and then the condition gives the period of a circular one loop. So magnetic force provides the central centripetal force. Okay, so this is the starting point. And then if you divide both sides by V, then you get this one. And the V over R is omega, angular velocity. And then this is given by this one. And the period of t is given by this relationship. This is the key. And then if you plug in those things, then you have this one. And the t is given, and we need to find out the magnetic field, right? So that this is the equation you need to work on. And then t is, note that everything should be in a conventional unit, second, kilogram, and coulomb. Okay, and then you get Tesla. Okay, that's it. This chapter is relatively easy once you understand the interaction between the charged particles and the magnetic field, and the wire and the magnetic field, and the loop, current loop and the magnetic field. And then finally, you have charges moving in a certain material, and then you have a Hall effect, that is balance between the magnetic field and the electric field to give the substances have a uniform uh, drift velocity that will give you the current. Okay, so basically it's very clear. Okay, and then hopefully you could understand all the problems. Thank you.